Alright guys, today we're going to talk about multiplying polynomials. And the way we have to start is we have to review our exponent rules. So anytime we're going to be multiplying variables together that have an exponent, we have to add the exponent. So for example, x to the n power times x to the m power would result in x to the n plus m power. So for example here, if we have x, there's nothing there, so there's an understood 1. And then we have x to the 4th power. So if we were multiplying those two guys, because they have the same base of x, all we would have to do is carry over that base of x and then add the 1 and the 4, and we would get an x to the 5th power. So that rule is kind of the basis of being able to multiply polynomials. So the beginning start of multiplying polynomials is a monomial times a monomial. So what happens here, we got 3x to the 3rd, 6x squared. What we can do is technically think of these things as separate terms, or individual pieces to the term, I should say. So we can rearrange this multiplication. So really there's 4 things being multiplied. So we can think of this as 3 times 6, and then the x cubed times the x squared as 2 different things. So we can kind of rearrange them. So what we can do is multiply the regular numbers together and get 18. And then we're going to apply that rule here. Since we have x to the 3rd power and x squared, we would end up with x to the 5th power since we're adding the 3 and the 2 together. Same exact thing we can do down here. We can multiply the regular numbers together. Now if you want to, you can always rewrite it like we did here. So you can say the negative 7 times 6 and then times x to the 4th times x. So negative 7 times 6, of course we have a negative times a positive, gives us a negative 42. And then x to the 4th times x, we would keep the x and then add the 4 and the 1 together and get x to the 5th power. And then last, we have 5x to the 3rd times x to the 4th. Now notice the 5 doesn't have anybody to multiply with because there's just really a 1 there, so 5 times 1 just stays 5. So the 5 just kind of comes along. And then x to the 3rd times x to the 4th, we carry that same base. And then 3 plus 4 gives us the 7th power. So that is basically how we would do a monomial times a monomial. All right, so now we're going to look at multiplying a monomial times a binomial or trinomial, and it ends up being the exact same case. So what we have to do here is we have to use what's called the distributive property. And what that means is we got to take the monomial on the outside of the parentheses and distribute it to each term that's in the parentheses. So what really is going on here is that we're trying to multiply this 5 times everything inside the parentheses. So what we end up doing is we take the 5, multiply it times the first term, and we get 5x. Then we take the 5 and multiply it times the 8, and we get plus 40. So that's how we would distribute that monomial on the outside. If we look at this next example here, it doesn't do anything different besides having that x on the outside. Now that 7x together gets distributed through the entire parentheses. This is still a monomial even though there's 2 things there, 7 and an x. They are considered one term. So if we multiply the 7x times the x squared, the 7 times 1 in front of that x squared still remains a 7. And then x times x squared, we're going to use the rule that we used a minute ago. We're going to add those exponents and get x to the 3rd power. Next, we're going to distribute the 7x to the 3x. So 7 times 3 gives us 21. And then x times x gives us x squared. And then last, we're going to distribute that 7x to the negative 4. So that gives us 7 times negative 4 gives us negative 28. And then x doesn't have anybody to multiply with, so he just kind of comes along. And then that would be our answer. And then last, we have negative 2x squared times that x squared. So we have negative 2, and then x squared times x squared. We're going to add those exponents again and get x to the 4th. And then we're going to distribute that to the negative 6. So we get negative 2 times negative 6 gives us positive 12. And then the x squared doesn't have any more x's to multiply with in that term. So we end up just bringing the x squared along. So that is the beginning part of multiplication and the distributive property. All right, the next thing we're going to look at is multiplying a binomial times a binomial. And essentially we're going to do the exact same thing. We're going to do the distributive property, but we actually have to do it twice. So we're going to take the first term here and we're going to distribute it to both the terms over there. So what we end up with is x times x gives us x squared, and then x times 4 gives us 4x. Now what we have to do is we have to take the other term in this first guy and we have to distribute him through both terms over here as well. So it's 2 times x gives us 2x, and then 2 times 4 gives us 8. So now if you notice, we're not finished here. We have two terms that are alike that can be combined. So what we do is just clean this answer up and we get x squared plus 6x plus 8, and then our answer is in standard form. So it's really the exact same thing as what we've done before with the distributive property, but now we just have to do it twice. Okay, so I want to show you with the same problem a method that was kind of developed so we don't forget to do both of the distributive properties there, and it's called the FOIL property. Okay, FOIL is an acronym. FOIL starts with the F, so this is first. And then the O stands for outer. The I stands for inner. And then the L stands for last. So if you look, the first terms are the first of each of the binomials. So the x and the x. So we would multiply them to get x squared. The outer terms are the two terms on the outside. So we have x and 4. So we get 4x. The inner terms are the two inside terms. So we have 2 and x there. And then the last terms are the last of each of the binomials. So then we have 2 times 4, which gives us 8. So if you notice, we have the exact same result in both ways. The FOIL method is nothing more than the distributive property twice, but it's an easy way to recognize and remember that we have to do the distributive property for both terms. So I always refer to the FOIL method anytime we're multiplying polynomials together or binomials together, and you'll hear me talk about that quite a bit. So let's look at another one. We're going to do x plus 7 times x minus 3. Okay, so we have two binomials. I want you to think FOIL as soon as you see those. So first, x times x gives us x squared. Outer is negative 3x. Inner, 7 times x gives us 7x. And then last is negative 21. So you notice what happens here is that when we use the FOIL method, the two terms that can almost always combine will be together in the middle. And that's another benefit of using the FOIL method. So we have x squared, and we're going to combine our like terms here. So negative 3 plus 7 gives us positive 4x, and then minus 21. So the FOIL method helps us to make those problems pretty easy. All right, let's take a look at another one. 2x minus 3 and x plus 1. So just because we have a number in front of the x there, we have a coefficient, we do not have to do anything different. It is still a binomial times a binomial. So we're going to use the FOIL method. First, 2x times x gives us 2x squared. Outer, 2x times 1. Well, we know anything times 1 doesn't change, so it's still just 2x. The inner terms, the two inside guys, negative 3 times x gives me negative 3x. And then last, negative 3 times 1 gives me negative 3. So again, notice my like terms are together there in the middle of that polynomial. So we can combine them and get 2x squared minus 1x minus 3. And that's how we would multiply those two together. All right, let's take a look at one more. We have x plus 5, and we have x minus 5. So, if we do the FOIL method here, we have first x squared, outer, negative 5x, inner, positive 5x, and then last, negative 25. So again, our like terms are here, but now notice what happens with this one. We have negative 5 plus 5x's, so they cancel each other out. And then we have minus 25. So this one is one of our special cases. And if you look back at the beginning of the problem, we notice we have the same numbers. We have x and 5, but we have 1 plus and 1 minus. And what this one is called is the difference of two squares. And the reason why it's named that is because we have a perfect squared here as x squared and another perfect square at 25, and of course difference meaning the subtraction. So we have the difference of two squares is the result when we multiply two polynomials together that are the same numbers, basically the same variables, and we have 1 plus and 1 minus. So that's very helpful, and we can kind of skip right to that if we see this. And it's even more helpful when we go in the opposite direction and we start to break these things back apart and we factor them. We can recognize this as the difference of two squares and know that it came from this exact situation. Now, I'm not a big shortcut and memorize kind of teacher, but I always tell my students that this is a very helpful shortcut to be able to become familiar with. You will see this all over every problem, or every set of problems, you'll see those there. You'll see that all over the ACT. You'll see this on any kind of standardized test. The difference of two squares is very common, so you will use this all the way through college if you make sure you get familiar with this. Let's look at one more, and then we'll finish up. We'll look at one more of the special cases. So what if I have x plus 6, x minus 6? So we still have the exact same setup as before, but now we've just changed the numbers. So if we recognize and understood what we talked about a minute ago, we can just jump straight to the first one squared minus the second one squared. Now if we're not recognizing that at the beginning, or if we're in a test and we're kind of stressing out and we don't necessarily see that, we can always revert back to our FOIL method. This is nothing that we cannot get to without multiplying this like normal. So if we go x times x, for the first, we still get x squared. If we go outer, we get negative 6x. If we go inner, we get positive 6x. And then we go last, we get negative 36. So even if I use the FOIL method, we still end up with our like terms in the middle, but they're going to always be opposite terms. So we have negative 6x, positive 6x, and they cancel each other out. That's why we don't have that middle term. And then the minus 36 comes along. So we still would end up with the difference of two squares.